Imagine that we have an ANOVA with one factor and three levels. What would that look like? It might look a bit like our pot trial. Our one factor would be the soil quality. The three levels would be the different kinds of soil quality, the good, poor, and the poor plus lime. With an ANOVA, we are trying to determine if there is a difference between the three means. So our H0 would take the assumption that there is no difference between the means. So we would write H0 as the first mean is equal to the second mean, which is equal to the third mean. Whatever value the mean is, that value is the same for all of them. In writing our alternative hypothesis, we write that the means are not equal. We don't write mean 1 is not equal to mean 2 is not equal to mean 3 because we don't know that they will all be different from each other. It could be that just some of them are different. If we were to reject the null hypothesis, H0, then we would know that there is a difference between our groups, but we don't know where that difference lies. In a one-way ANOVA, we are looking for a main effect due to the one factor, in this case the quality of the soil. We can't investigate interactions in a one-way ANOVA because there is only one factor applied to each population. After we have stated the hypotheses, we next choose a level of significance for alpha, just as we did earlier. We're remembering that alpha is the probability level at which we will mistakenly reject the null hypothesis when it is actually true. That is, when we say there is an effect due to the treatments when actually there isn't. Alpha equal to 0.05 has a 5% chance of having a type 1 error. 0.05 is a common choice for alpha, as is 0.01. Next, for the ANOVA, we need to calculate the degrees of freedom. In our computer package, this will be done for you, but it's quite handy to know what they mean so you can read and understand their ANOVA output table. The small n is the number of observations in each treatment. Capital N is the total number of observations in the dataset. So in this example, we have 5 observations in each level of soil quality. So there are 3 levels of soil quality. So 5 times 3 gives us a total of 15 observations. We denote the number of levels for a factor as the letter lowercase a. Remembering that this is a one-way ANOVA, we are looking at the main effect of soil treatment. So we have one factor, the soil treatment, and we have 3 levels of that factor. So in this case, A is equal to 3. The degrees of freedom that the ANOVA will use in calculating the variation between the treatments is given by the number of treatments minus 1. So we have 2 degrees of freedom between treatments. We use the total number of observations minus the number of levels to give us 15 minus 3 equals 12 degrees of freedom within the data. The total number of degrees of freedom used in the analysis is the sum of the degrees of freedom within and between the treatment groups. So this gives us a total degrees of freedom of 14. When we calculate a one-way or single factor ANOVA in Excel, we can see that the first line tells us the type of ANOVA we have calculated. Then we have a summary of all the data from our table. It tells us the 3 levels of treatment or the 3 treatment groups. The count is how many observations are included in each group. The sum is the sum of all of those observations in each group. Likewise, the average and the variance is calculated for the values belonging to each group. Under the summary data is the ANOVA results for that data. We can see the variation is split into variation between groups and variation within groups. SS is the sum of squares between groups, within groups, and in total. The total is given by adding the sum of squares within and the sum of squares between groups together. The degrees of freedom we have already discussed. We can work out by looking at the ANOVA table how many treatments were included in this analysis, because we know the degrees of freedom between treatments is the number of treatments minus 1. The degrees of freedom is 2 for between groups, therefore the number of treatments used in this analysis was 3. The mean square is the sum of squares divided by the degrees of freedom. That is, the mean squared for between groups is the sum of squares of 14.4 divided by 2. The mean squared for within groups is 21.2 divided by 12. The F critical value on the far right side helps us to decide, along with the p-value, whether we reject the null hypothesis or not. Remember, the null hypothesis is telling us that all the means are the same and therefore there are no treatment effects. If there are no treatment effects, F will be equal to 1. If there are differences due to treatment, the F value will be greater than 1, but we then compare it to the F critical value provided in the table. If the F value is greater than F critical, we reject H0. And just a note on how we calculate F, we take the mean squares of between groups and divide it by the mean squared of within groups. We now know that the F value is greater than the F critical value. The P value tells us how likely we are to get this result if the null hypothesis is actually true. That is, the F values tell us that the means are not all the same. The P value tells us the probability of this result from any chosen sample if the three means are the same, just like with the grape example. The p-value from this ANOVA is 0.044. This tells us we are likely to get the result that says the means are different when they are actually the same, only 4.4% of the time. Our p-value is also below the 0.05 level to which we set alpha for this ANOVA. So yes, on both accounts of the p being low and the F value being greater than the F critical value, we can reject the null hypothesis. Now that we have taken that last step to decide to reject the null hypothesis, this is a statement that we might put in our report about the significance of results with respect to the sample that was tested and the F and P values that were used. So we might say the three treatments differed significantly with respect to height or dry matter yield or bunch weight. At an F of 2 degrees of freedom between groups, 12 degrees of freedom within groups. So we put the 2 degrees of freedom values in brackets following the F, where the F is equal to 4.07 and P was set to less than 0.05.